with the piecewise function, knowing what we know about the definition of continuity, we're going to start by finding f of a. In this case, it's a continuity test when x is 6. A is 6. So we're going to take 6, and we're going to plug into the function. Now, we have to plug into the function where the function is defined. 6 is greater than 2. So if 6 is greater than 2, that's going to sync up with my second piece there. Meaning I'm going to take 6 and I'm going to plug into the second piece, get 5 minus square root of 6 minus 2. Of course, square root of 6 minus 2, square root of 4 being 2. You've got 5 minus 2 here, so that's going to be 3. F of 6 equals 3. So you start on these continuity tests by finding whatever f of a is, and then we focus our attention on the limit. Now, we could refer back to the graph for a better understanding here, but basically we're taking the limit as x approaches 6, we're applying it to the function, and with what we understand about limits, left-hand side, right-hand side have to match up. If x is approaching 6, since this second piece here is where x would be 6, right? It's going to be greater than 2, then we could say with reasonable confidence, from the left and the right, we're only going to be traveling on this piece, right? We're not going to have to worry about any breaks. So if we can conclude that with reasonable confidence, we take 6, we plug into that piece of the function, which is the second piece, and we get, well, we get 3 back, right? It's the same as what we got up here. So what we're trying to show, now that we've done the limit, we're trying to show that the value we get for the limit and the value we got back here, for when we took x and we plug in the function, are the same thing. If they are, we can draw a conclusion that f is continuous at this x value of 6 that we just explored. And if we're going to state that, we got the mathematics to back it up, but we want to make sure it's clear what the mathematics is justifying, so we need a little extra. We'll give a reason, because the limit as x approaches 6 applied to the function, so this second part here, that equals f of 6, this first part right here. That's why it's continuous. And that's consistent with the definition of continuity. So same piecewise function, same sort of routine here we're going to follow to try to show that this is continuous. Like we did on the last one. Start with f of a. What is a here? A is 0. So take 0, plug into the function. You have to plug into the piece of the function where 0 is defined for x. So 0 is less than 2. That means I'm going to plug in up here to this piece. So f of 0 equals 1 over 0. Uh-oh. That doesn't work, right? So f of 0 does not exist. It's undefined. Now here's the good news when you run these continuity tests. You're trying to show that these two ideas are equal, meaning I need to get values back for both. I already found that for one of the parts I didn't get a value. So this must not be continuous. I can go right to my conclusion. I don't even have to look at the limit part. I can say, therefore, f is discontinuous at x equals 0 because, well, it's discontinuous because I didn't get a value back when I took 0 and plugged in the function. F of 0 does not exist. Yeah, if we run a continuity test where x equals 2, this is going to be more intriguing because x equals 2 as it relates to this function, the way it's defined, that's going to be around the breaking point here for the two pieces. So let's be consistent. Let's start the same way we have so far. Start with f of a. So f of 2. Got to plug in where the function is defined for x being 2. So that would be where x equals 2. X is greater than or equal to 2 for the second piece, right? So I'm going to plug into the second piece. Be 5 minus square root of 2 minus 2, so that's going to be 5 minus 0, or 5. So f of 2 gives us a value, unlike the last one. Since it gives us a value, we move forward. As we move forward, we explore the limit next. As we consider the limit, where x approaches 2, apply to this function, I go back to what I referenced on the first example. I talked about you got to understand the left-hand limit and the right-hand limit are going to match up. Now, with that first example, it was nice because we could focus our attention on one piece. We knew our x value had to be only on that one piece. But here, if you take the limit as x approaches 2 from the left, and you take the limit as x approaches 2 from the right, we actually have two pieces to consider. From the left, we're talking about values that are less than 2. X is less than 2 when the function is 1 over x. So my left-hand limit, I'm going to apply to 1 over x. And for the right-hand limit, we're talking about values that are greater than 2. So that's this piece. I'm going to apply my right-hand limit to the second piece of the function, being 5 minus square root of x minus 2. Now, once I specify my pieces down here, I can go ahead and plug in this value of 2 to each of the respective pieces. When I plug in 2 to this first piece, I get 1/2. 2 to the second piece, well, we already saw what happens up here, we get 5. As we understand limits, if these do not match up, the limit does not exist. So is it possible for the limit as x approaches, in this case 2, applied to f of x to equal f of 2? No, because we didn't get a value back from this part. So therefore, f is discontinuous at x equals 2 because, well, what failed us? The limit. It failed us. The limit as x approaches 2 applied to the function does not exist.